Wayne has 3 green buckets, 2 red buckets, and 3 blue buckets, and 3 yellow buckets. He randomly distributes 4 hockey pucks among the green buckets, with each puck equally likely to be put in each bucket. Similarly, he distributes 3 pucks among the red buckets, 2 pucks among the blue buckets, and 1 puck among the yellow buckets. Once he is finished, what is the probability that a green bucket contains more pucks than each of the other 11 buckets? Okay, so green, red, blue, and yellow. So let's start with the yellow. That seems to be the easier one. There's 3 buckets, right? So the only way is 1, 0, 0, 0, 1, 0, or 0, 0, 1. That's the only way to place the 1 puck. Either you put the 1 puck here, or you put the 1 puck in the second bucket, or you put the 1 puck in the third bucket, right? Because you got 3 buckets here. So these are the only scenarios. So that's pretty straightforward. Now let's go to 2 buckets. 2 pucks, I should say. 2 pucks. Well, you can have 2, 0, 0, 0, 2, 0, 0, 0, 2. Or you can have 1, 1, 0, 1, 0, 1, or 0, 1, 1. And I think those are the only ways. So let's keep a tally here. Here there was 3 ways, and here there's 6 ways. But this is the part that makes the question a little bit tricky. Yes, there's 6 ways, but some of these have more than 1 permutation. For example, this one, and I'll write the number of permutations in a different color, has 2 permutations, and so does this, and so does this. For example, let's talk about this one. If I call my pucks P1 and P2, if I use a 1, 1, 0 scenario, I can have P1, P2, and 0, or I can have P2, P1, and 0. So do you see why it's 2? So I'm not going to write out all the permutations like I just did. That would take a little bit too much time. But I will write out the number on the side. So when you count up all these, you get 9 down here. 2, 2, 2, and then 1, 1, 1, like that. Okay. Now let's talk about red. Red, 3 pucks. So you can have 3, 0, 0, 0, 3, 0, 0, 0, 3. Or you can have 2 and 1. So you can have 2, 1, 0, 2, 0, 1, 1, 2, 0, 1, 0, 2, 0, 1, 2, 0, 2, 1. Or you can have 1, 1, 1, like that. Okay, now time for the permutations. These guys will just have 1, but this one will have 3. All these guys will have 3 permutations, and this one has 6. So when you add it all up, it looks like 24 plus 6, which is 30, 6 times 3 is 18. 18 plus 6 is 24. 24 plus 3 is 27. So 27. And now we got the last one. 4 hockey pucks go into the green buckets, those 3 green buckets. So what are our possible ways of doing that? Well, you can have 4, 0, 0, 0, 4, 0, 0, 0, 4. Or you can have 3 and 1. So 3, 1, 0, 3, 0, 1, 0, 1, 3, 0, 3, 1, 1, 3, 0, 1, 0, 3. Or you can have 2, 1, 1. So 2, 1, 1, 1, 2, 1, or 1, 1, 2. Or you can have 2, 2, and 0. 2, 2, 0, 2, 0, 2, and 0, 2, 2. Okay, now let's write the permutations. The first 3 only have 1, but these guys all have 4 permutations. 4, 4, 4, 4, 4. The next have 12 each. 12, 12, 12, 12. And then these ones have 6. So in total, we have 81 for this one. Okay, so now let's talk about how do we get this? The probability that a green bucket contains more pucks than each of the other 11 buckets. All right, well, let's talk about that. So, for example, if I choose something like this, one of these buckets has 4. No other scenario anywhere else is there 4. So no matter what I chose anywhere else, I'm guaranteed that a green bucket, namely this one, will have more pucks than each of the other 11 buckets. So I want to choose these guys. So how do I do that? Well, 3 of those 81. There's 3 here and there's 81 total if you count all the permutations. Then from this I can choose any of them. So I can choose 27 over 27. From here I can choose any of them. 9 over 9. And from here I can choose any of those 3. So 3 over 3. And you multiply them. So this is one scenario. And this is just 3 over 81 because all those other guys are just 1, right? Okay. Now let's talk about another way of doing it, which is you would choose any of these. Since these have a bucket with 3, if you choose other scenarios that have less than 3, it would work. So if I want to choose those, that's what? 4 times 6, so 24 of the 81. So 24 of the 81. But from here, I can only choose these guys. So because if I chose this, it would have a 3 and that would not work. So how many of these are there? There's 3 times 6, which is 18, plus 6, 24. Times 24 of the 27 total. Here, I can choose any of them. So that's the full 9 over 9. And then here I can choose any of those 3, so the full 3 over 3. So that is 24 times 24 over 81 times 27. Now, any other scenario? Well, let's see. These ones not going to work because those have a tie. There's no one individual bucket that has more. So those ones won't work. But these ones I think we can work with. So if I choose those, that's 3 out of the 81. And then I've got to make sure that everything else only has 1s. So let's see here. This is the only one that has 1s. So 6 of those out of the 27. And these ones. So that's another 6 of the 9. And all of these should be okay. So 3 of those 3. And this, therefore, is 38. Sorry, it's... Oh, when I chose these guys, I forgot the permutations. It's not 3, it's 12, 12, and 12, so it's 36. So that 3 should have been 36. So as you can see, a little bit challenging there. Okay, so that's right. So that's just 36 over 81 times 6 over 27 times 6 over 9. All right, so now we're ready to add them. So we have to add them now. We have to add this, this, and this to get the full probability. So 3 over 81. Let's reduce it. Let me just write it out first. 24 times 24 over 81 times 27. And then 36 times 6 times 6 over 81 times 27 times 9. Okay. This is our full probability. Okay, I can reduce this as 1 over 27. We can divide through by 3. So if I do that, it becomes 8. And then the 81 becomes 27. And then this one, I can divide through by 3. And I get 8 over 9. And then similarly, on this guy, this will, if we divide through by 3, we will get 2 over 9. Divide through by 3 here, and we get 2 over 3. And divide through here by 3, and we get 12 over 27. I think that will go into there to give 4. And anything else, I think that's pretty much it for now. And we're just going to need to get a common denominator, which I think is 27 times 9, which is 243. So that's going to be top and bottom by 9. So 9 plus 64 plus 4 times 2 times 2, which is 16. And therefore that is 9 plus 64 plus 16 is 89 over 243. So there we go. 89 over 243 is the answer to this question, and that would be B. In the coin game, you toss 3 coins at the same time. You win only if the 3 coins are all showing heads or if the 3 coins are all showing tails. If you play the game once only, what is the probability of winning? If you toss a coin 3 times, you have the possible scenarios. They can all turn up tails, or you can have 2 tails and a head, like this, TTH, THT, or HTT. You can have 1 head and 2 tails, like this, THH, or HTH, or HHT. Or you can have all 3 heads, like this. So as you can clearly see, when you toss a coin 3 times, there's 8 different possible ways that it can turn up. Now, this game you win if you get all heads or all tails. So that means you win if you have this scenario or this scenario. So of the 8, the probability of winning, there's 1 and 2. So 2 of the 8 scenarios you win. And therefore that's the probability. And you lower this to lowest terms, of course, and that's 1 over 4. So number 22, the answer is B. Five monkeys are seated around a table. Their seats are labeled PQRST in clockwise order, as shown. The 5 monkeys are randomly numbered, monkey 1, 2, 3, 4, and 5. Monkey 1 remains in its seat. The remaining 4 monkeys then sit themselves in the remaining seats so that they are seated in clockwise order as monkey 1, 2, 3, 4, and 5. What is the probability that the monkey originally in seat R moves to seat P? We have a few scenarios here, and each scenario I will discuss, and then we'll try to figure out the probability for each. So first, let's label all of these according to the way they've labeled it, PQRST. Now let's talk about monkey number 1. If monkey number 1 is at position R, right here, then because he remains in his seat, nobody is actually moving to seat number P. Because normally there has to be a rearrangement. And he's going to stay there, so the guy in seat R doesn't move. So nobody's going to P. Maybe some other monkey is, but he's not. The question says that the monkey in seat R has to move to seat P. If M1 is in seat R, he will not move to seat P because he remains in his seat. So if this is a scenario where M1 is originally sitting in seat R, the probability is 0. Because he's going to remain in seat R. Similarly, the next scenario is if monkey 1 is sitting in P. He remains in his seat. So whoever's in R, if they move around, that's fine, but they're never going to be able to move to P because P is occupied by M. So in this scenario, the probability of somebody moving from R to P is also 0. Nobody can move into seat P because monkey 1 is in that seat and he remains there. So the only way we're going to be able to extract a probability in this question is if monkey 1 is either here originally, seat Q, or seat S, or seat T. So we'll talk about each of these one by one. If monkey 1 is in seat Q, we want the guy who's here to move to here. Okay, so we got to do a little bit of thinking here. Who's going to go to P if it's going to be arranged in clockwise order as 1, 2, 3, 4, 5? Well, 1, 2, 3, 4, 5. Well, it's got to be monkey 5. Once the clockwise order happens, monkey 5 is going to end up in P. So that means he must originate at R in order for this sentence to be satisfied. The monkey originally in seat R moves to seat P. He was sitting in seat R, but then after the rearrangement happens, he moves to seat P. That is one scenario. So what is the probability of this? Okay, first we have to look at the probability that M1 is in Q. There's 5 seats. We have to put him in one of those 5 seats. So the probability of that happening is 1 over 5. That's the probability of monkey 1 to be placed in seat Q. Then, in addition to that, monkey 5 has to have been placed in R. But be careful, this is fixed. So now monkey 5 has to choose between these 4 seats. And the probability of therefore putting monkey 5 in one of those 4 seats is 1 over 4. So that probability is 1 over 20. Okay? So a little tricky, not super tricky, but a little tricky in my opinion. Not the hardest, but definitely not the easiest. Somewhere in the middle. Okay, so we've done with this one. This circle is done, this circle is done, this circle is done. Those were zeros, so they don't contribute anything to our probability. Now let's go to the next scenario. The good news, you probably already figured this out, is that the next scenario is identical. We want monkey 1 to be in S, right? So there's 5 choices for the seat for monkey 1, and of those we want S, so that's 1 over 5. The probability of putting monkey 1 in seat S. Then, now we have to think about this. We want some guy to go from R to P. Well, when the arrangement happens, it's got to be monkey 2, monkey 3, monkey 4, monkey 5, like that, right? So monkey 3 has to end up in P. So that means he originates in R. See, he originates in R, but then once the rearrangement happens, because it's done according to clockwise order, 1, 2, 3, 4, 5, he's going to end up going to P. So what's the probability of that happening? Well, it really just means what's the probability of having monkey 3 originally sit in R? Well, since S is already taken, he's got 4 possible choices, and of those 4 possible choices, he has to choose one. So the probability of putting monkey 3 in one of those 4, which is R, is 1 over 4. And that again is 1 over 20. And then finally, we've got the last scenario. Monkey 1 is now fixed at T, but we want the guy who's originally there to eventually end up here. Well, when you do the rearrangement, it's going to be monkey 1 there, and then 2, 3, 4, 5. So monkey 2 is going to end up in P, so he must have to originate at R. He's sitting there, but then after the rearrangement happens, he ends up going to P. So in the same way, what's the probability of choosing seat T for monkey 1? Well, 1 out of 5. And then what's the probability of choosing seat R for monkey 2? Well, he had only 4 choices, so it was 1 out of 4. And that again is 1 over 20. So to get the total probability, we have to add up all the probabilities. 0, 0, 1 over 20, 1 over 20, and 1 over 20. And when you add up those probabilities, you get a grand total of 3 over 20. And therefore, number 22, the answer is C. There are 4 people in a room. For every 2 people, there is a 50% chance that they are friends. 2 people are connected if they are friends, or a third person is friends with them both, or they have different friends who are friends of each other. What is the probability that every pair of people in this room is connected? We have 4 friends. I'll call them A, B, C, D. And there's the following pairs. We have A and B, A and C, A and D, B and C, B and D, and finally C and D. Those are the 6 possible pairings. And now we have to figure out if they are connected or not. And the best way to do this question is with diagrams. So I will explain all the diagrams. And we're going to make a little bit of a table here. The first table is going to involve whether or not they are all connected or not. And if so, how many friendships are involved. So hopefully this will become clear as I explain it. So the first question is, all connected? Yes or no? The next is the number of friendships. So let's start off with the most basic one. And I'm going to draw a diagram to illustrate it. So this doesn't have to be a work of art. So here we go. The first one is if you have all 6 friendships, meaning all of them are friends with each other. So all of these are basically friends. Now that can be illustrated really nicely in a diagram as follows. You make a little box like this, and each of these represents a friendship. So this is friend A, B, C, and D. If 2 people are friends, they will be connected to one another. So A and B are friends, and as you can see, there's a line between them. A and D are friends, there's a line between them. B and C, C and D, D and B, A and C, all of them have a connection. That shows that they're all friends. That's what this diagram hopefully is showing. So there's 6 friendships, and all of them have a line with each other. 1, 2, 3, 4, 5, 6 lines, 6 friendships. And are they connected? The answer is yes. They are connected. They satisfy at least one of these. Okay? So that is just kind of simply explaining it. Now, if you're still not convinced, I'll break it down a little bit further, one at a time. So first I'll start with the first one. If 2 people are friends, how can you be illustrating them in a diagram situation? Well, if 2 people are friends, you just draw a line between them. And let's say those 2 people are A and B. There you go. That takes care of this one for our diagram purposes. The next one is a third person is friends with both of them. So they're not friends. So you got a situation where you have A and B. They're not connected. There's no line between them. But there is a third friend that they're both friends with. So let's say it's C. So there will be a line from B to C and A to C. That is what this is describing, the second one. A third person is friends with both of them. C is friends with A, is friends with B. But B and A are not friends with each other. But it doesn't matter for our connection purposes. This is still qualifies as connection. It is in the definition here of being connected. The third scenario, they have different friends who are friends of each other. Okay, what does that look like in a diagram? Well, let's draw it. Here's A, B, C, and D. It looks like the following. A and B are not friends, but A is friends with D. B is friends with C, but D and C are friends. Okay, that takes care of the third guy. So anything that looks like that means that A and B are connected. So it's pretty obvious that this satisfies pretty much, this sole first one by itself. We don't even need to worry about anything else. Okay? So if you get that, if that is clear, let's move on. Now we move on to the next scenario. The next scenario is where the number of friendships are 5. And what that basically means is that instead of 6 lines, 1, 2, 3, 4, 5, 6, we're only going to have 5 lines. So 1 line will be missing. And what that basically means is that out of the 6 lines, you choose only 5 of them. So let me repeat that. In the first diagram, you know how you had 6 lines, 1, 2, 3, 4, 5, and 6. We only want 5 friendships. So instead of 6 lines, we want 5 lines. So out of the 6 lines, I choose 5. This is what that means. 6 choose 5. And 6 choose 5 is 6 factorial over 6 minus 5 factorial over 5 factorial. And if you do the math, that just comes out to 6. Okay? So there's 6 ways of having a situation of only 5 friendships. Now, if you do that, are they all connected? Well, let's see. Let's draw a diagram and see. Diagram, I will draw and then I will explain it. So this is going to be our diagram. And I only want 5 lines. So far I've drawn 4. Here's a 5th line. Does this connect everybody? If they're connected, they will be joined in some way. You'll be able to get from one friend to the other friend somehow. Like for example, in the first one, because A and B are joined directly, you can get from A to B on that line. But in the second one, A and B are not joined, but you can get from A to B through C. In the third one, A and B are not joined, but you can get from A to B through D and then through C. So they are connected if you can get from any one to another one through some path. And you can get from A to D, you can get from A to B, you can get from A to C, and so on, right? I mean, this basically means that everything is connected. So the answer here is yes. So far, there was only one way of making that box. So that's 1. There's 6 ways of making a situation where you have only 5 sticks, 5 connections. So that's 6. Okay. Now, some of you might say, well, I know another way of drawing this diagram. What about if you had something like this? And then you drew the sticks like this, the 2 diagonals, but then you got rid of 1 stick like up here. That's a way of making 5 sticks, and you're absolutely right. If you came up with that way, that's definitely a way of doing it. In fact, there's 2 ways of making this box and 4 ways of making that box. So that's why the total is 6. Okay, so far so good. Let's move along. Now the next one is 4 friendships. So what that means is instead of 6 sticks, I want 4 sticks this time. In a very similar way, from 6 possible sticks, you would choose 4 this time. And that is 6 factorial over 6 minus 4 factorial all over 4 factorial. And when you do that math, you get 15. So we got more here. We got 15 ways of making a diagram that has only 4 sticks, and that represents 4 friendships. Now, are they all connected though, if you have 4 friendships? Well, let's see. Let's draw some possibilities. Let's draw this one here. That's 4 sticks. Are they all connected? Can you get from any one of these to the others? And the answer is sure you can. That's definitely a connection. How about another diagram that has 4 sticks? Something like this. 1 stick across the middle, like that, but then 1 stick removed from one of the sides. That's 4 sticks, right? 1, 2, 3, 4. Is this connected? A, B, C, D. And the answer is yes. You can get from any letter to any other letter with a path. If you want to get from A to C, you can. If you want to get from A to B, you can. So this is also connected. So I encourage you to kind of go through this on your own and convince yourself, just don't, take it at face value. So this is also a yes. Now we get into the stuff that is a little bit more trickier. Now, I want to just take a pause here and say that these 15, there's a few more diagrams. I'll let you do that. I want you to come up with the other diagrams, but I will guarantee you that all 15 of them will be able to show connections. And those other diagrams, you know what? I'm a nice guy. I'll give you a hint. There's another one that has basically the two diagonals, but then you're just removing two sides like that. That's 4 sticks, right? 1, 2, 3, 4. And then there's others as well. And like I said, I want you to do that instead of me having to spell everything out for you. Okay, now we get to the last three. The last three are where the question really not necessarily becomes extremely difficult, but that's how you're going to arrive at the right answer. Now I'm going to do the last two first, which is number of friendships is going to be 3 and 2 and 2 and 1 and 0, right? Those are my possibilities. Well, with 0, what that means is that basically you have just 4 dots, A, B, C, and D, and there's no sticks. Like that. No sticks. So are they connected? Well, definitely not, right? But how many of these do you have? From 6 possible sticks, you choose 0. And 6 choose 0 as 1. But that doesn't need to be counted because they're not connected. How about if you have one friendship? One friendship is a very easy diagram to draw. It's A, B, C, D, and you just have one stick. So somewhere, is this connected? Well, no. D and C are not connected, and D and A are not connected. How do you do that? From 6 sticks, you choose 1. And there's 6 ways of doing that. But it's not connected. How about 2 friendships? 2 friendships, again, pretty easy to draw an example. A, B, C, D. I got to use 2 sticks. How about that? That and that. That's 2 sticks. Are they connected? No. A is not connected to D. C is not connected to B. How many of these? From 6, you chose 2 sticks. And 6 choose 2 is 15. Now we get to the heart of the question, which is 3. 3 friendships is what decides whether you're going to get this question right or wrong. 3 friendships, and I think I'm going to need a little bit more space, so I'll move it over, has 5 different scenarios, unfortunately. So I'll draw them out. We got this one, and then, well, obviously I'm going to have to edit these. Okay, so the first one is 3 sticks, like that. Now, are these connected? Well, you tell me. If this is A, this is B, this is C, and this is D, is everybody connected? Think about it and let me know. And the answer is yes, they are, right? Because you can get from A to D, A to C, A to B, in any sort of path like that. So there's 4 of these guys. Now, what is the total? I didn't do that yet, right? 6, it's going to be from 6, choose 3, if I'm following the same pattern as all the other ones. And 6 choose 3 is equal to 20. So I have to figure out of these 20, how many of them are going to have a yes. And then some of them are going to have a no. This is the only one that splits up into yes, no, which makes it kind of challenging. Okay, let's move forward. Let's go to the next one. The next one, I just do a box, but that's not what it looks like because obviously that's too many sticks. The next one, what I really meant to draw is this. 3 sticks like that. So this is A, B, C's out here all by itself, and then D. Are these connected? And I am certain that you by now will be able to figure out that no, this is not connected. Now, how many ways of making these? There's 4 ways of making something like this, right? So these 4 are not connected. So the ones that are connected, I will circle. Okay, now let's go to the last 3. The last one is going to have basically a scenario like this, where you draw that and you get rid of those 2. So that means you have now 3 sticks, correct? So this is A, this is B, this is C, and this is D. Is everybody connected here? And the answer is yes, they are. So here's another 4 that's connected. The second last one is going to look like this, but I can only have 3 sticks, so I've got to get rid of a few. Got to get rid of this one, and I'll get rid of this one. So it becomes sort of a Z pattern. And are the Z patterns connected? Well, let's see. A, B, C, D, and the answer is yes. So this gives me 4 more. And then the very last one, that one is going to look like this. You're going to have 2 diagonals, but I've got to get rid of one. Actually, got to get rid of 3. I get rid of this one, and this one. There you go. So it becomes sort of an X with a hat. And let's just label this. So this is A, B, C, and D. Are these connected? And the answer is yes. So of these 20, the only ones that were connected are this 4, this 4, this 4, and that 4. So 16 of them are yes. And this guy is a no. All right, so that's what I'm going to circle. So now what we have to do is count up all the yeses and then divide by the total. So I think I can do that. Let's just do it here, keep myself on the same page. So in any probability question, the denominator is the total. So what's my total, first of all? Well, I got 1, 6, 15, 20, 15, 6, and 1. Those are my total cases. When you add that up, you get 64. So that's my denominator. Numerator is the yeses. So this was a yes, that's 1. This was a yes, that's 6, we're up to 7. This was a yes, that's 15, we're up to 22. This one was a yes, 16. So now we're up to 38. And that's it, right? Yeah, that's it. Because everything else was a no. This is no, this is no, this is no, this is no. The 38 is my numerator. And that's the answer, 38 over 64. I think they've lowered it to lowest terms, 19 over 32. So let's go back, 19 over 32. For number 25 would be choice D. Three real numbers x, y, and z are chosen randomly and independently of each other between 0 and 1 inclusive. What is the probability that each of x minus y and x minus z is greater than -1/2 and less than 1/2? Let's draw the x, y, z axes and a diagram. This is, of course, the x-axis, and this is the y-axis, and this is the z-axis. Our boundaries, of course, are 0 to 1 for everything, so that's 0 to 1. This is obviously 0. Here's 1, and here's 1. Now we take into consideration our restrictions or conditions. So the first one is that x minus y is between -1/2 and 1/2. And the second one is that x minus z is between 1/2 and -1/2. So let's draw these. First, let's look at this inequality. So that basically would mean that y is less than x plus 1/2. And we can quickly draw that. X plus 1/2. So for example, when x is 0, we're really just looking at the xy plane now. When x is 0, y is 1/2, so approximately here. When x is 1/2, y is 1, so approximately here. And then we can connect those two lines, and let's do that. So here we go. So remember, we're just looking at the xy plane right now. Later we'll look at it with the z-axis. Now let's look at this part. That would basically mean that x minus 1/2 is less than y. So again, let's plot that. When x is, say, 1/2, you're going to have a 0. So that's going to be approximately x minus y less than 1/2. So for example, when x is 1/2, y will be 0. So that's right here. When x is 1, y will be 1/2 right here. And then connect those lines as well. So as you can see, we want the area that is in between those two lines, because y's got to be less than this and it's got to be greater than that. Okay, that it's a cube, so that's going to be extrapolated all the way to the other side. So that's the key in this question, that you've got to be able to figure out the three-dimensional aspect of it. So we have to connect this, so let's do so, all the way to the other side. So there we go, and then I join them all. So that basically means that we've sliced off a section of each side, as you can clearly see. I hope this is drawn in a way that you can see that. Now that part is actually pretty straightforward, because all I have to do is just really look at the XY plane, and I'll draw the XY plane here, let's say. And you don't even need that big of a diagram, just something like that is sufficient. And then really what I did is I just chopped off corners like this. And you can easily figure out the volume of that. So the entire cube or face is 1 times 1. And then I chopped off this guy and I chopped off that guy, because that falls outside of our boundaries that these inequalities create. So this one would be a triangle, 1/2 base times height, 1/2, 1/2, and 1/2. And then similarly, this is also a triangle, 1/2 base times height, with the base of a half and the height of a half. So this is 1 minus an eighth plus an eighth, which is a quarter. So 1 minus a quarter, so 3/4. But that is just the shape that basically is 2D. We want the 3D version. Well, the 3D version, to get the volume, all you have to do is just multiply by the height. And the height from there to there is just 1, because it's 1 on the z-axis. So you take that 3/4 and you just multiply by 1 to get the volume of that shape. And that, of course, just gives me 3/4. So this 3/4 is a very important part of the question. We'd be done if there wasn't another inequality. But we do have another inequality, and that is x minus z now has to be between a half and negative a half. Okay, in the same way, let's plot this. So this gives me two equations. The first one it gives me is that x minus a half is less than z, if I'm looking at that one. And then if I'm looking at this one, it will give me that z is less than x plus a half. And in a very similar way, let's plot those. So this time it's the z and the x-axes. So when x is a half, z will be 0. So that's going to be right here. And then when x is 1, z will be a half. So that's approximately here. So we just connect those from there to there, approximately like that. And then this one here, when x is 0, it'll be a half for z, and when x is a half, it'll be 1. So again, we're connecting it like that. So as you can see, in a very similar way, we have chopped that into an area, and we of course have to just look at that section. So let me draw the same thing on the top. So that's going to be approximately here to here, and from here to here. And let's now connect those. So we're connecting it to kind of show what happens. So there we go. All right, so I think that's pretty decent. All right, so now we have to figure out what's going on. Well, the first part, right, we figured out was 3/4, and that's great. But now from that 3/4, I have to cut out these shapes. And this shape, this is one of the faces, along with this right here. I'm chopping that off. So I hope that makes sense. I'm chopping it off from that side, and I'm chopping it off from this side, because we can only keep what's in the middle because of these inequalities. So, all right, not a problem, right? You just take this and then subtract from it those two shapes. But it's not that simple. Why? Because those two shapes also have this part missing, as you can see there. So it doesn't become that easy. So let's rationalize this. The first thing, of course, was we take our 3/4, which is what we got. And then from that, we have to subtract something. And that something, of course, is this triangular prism, right? That's what this is. And there's two of those guys, so I have to subtract those two triangular prisms. So 2 TP triangular prisms. But before we subtract the triangular prism, we have to subtract this segment of it. This segment that is not part of the triangular prism. See what I mean? And that is actually a square base pyramid. Square base pyramid. So that square base pyramid, I think that's the most challenging part. I think most people can get to here, but then it becomes challenging as to what is this shape right here. So let's illustrate that. Let's talk about that a little bit before we do this calculation. So we have this triangular prism, right? Right there. And what we did was we take that triangular prism and we put it here because we have to subtract that from the 3/4. No problem. But there is a problem because we then have to slice that, as I tried my best to illustrate here in the diagram. And that's what this does. It slices that triangular prism. And when you do, you get left with this shape. Now, what is that shape? That is the square-based pyramid. As you can see, this is the square base, and the rest of it is in the shape of a pyramid. So now we can figure this out. So this is 3/4 minus 2. The triangular prism, the area is up here, the big one. That is the triangle, and then this is the height all the way down. It's the area of the triangle, which is 1/2 base times height. The base is 1/2, the height is 1/2. So 1/2 times 1/2 times 1/2. And then you multiply that by the height, top to bottom, which is a 1 in this case. Okay. The square base pyramid, this guy, which is where that slice occurs right there. Above the slice, we have to get rid of that. How do you figure out that area? Well, the area of a square base pyramid is 1/3 times the base times the height. So 1/3 times the base. The base is a square. That's why it's called a square base pyramid. And the dimensions of that square are 1/2 and 1/2. So the area would just be 1/2 times 1/2. And then the height is from here to here, and that is also 1/2. So that is also 1/2. So there we go. We have this question done. Now all we have to do is just figure out that math. So that's going to be 3/4 minus 2, and that looks like 1/8 minus 1/24. Okay, so 3/4 minus 2, that is, get common denominator, 3 and 3, 3 minus 1, so 2/24. And therefore this is 3 minus 4 over 3 over 4 minus 4/24. And that looks like we can just get a common denominator. Multiply top and bottom here by 6. So that'd be 18 minus 4/24. That is 14/24. In lowest terms, 7/12. 7/12 is the answer. I encourage you to, and I'm being serious, get some Play-Doh. And Play-Doh, or sometimes it's referred to as plasticine, you can get these at any kid store, toy store, and then just make shapes. And then take a knife and cut through them. And I promise you that will help you, because sometimes it becomes very difficult to visualize it. Or if there's some computer software, perhaps that might be even better. So 7 over 12 is the answer to number 25, and that would be B.